Well, let's see what you need to know for your Unit 3 exam. So Chapter 9 talked about kind of the leftovers in our solar system. Asteroids and comets didn't make it to form either the sun or planets. The main difference is that comets are both rocky and have an icy component to them. And as we talked about in class, the reason that they have that icy component was because they formed past the frost line where actually ices could go ahead and solidify. What else we got? Well, we got the M's. We got meteoroid, meteor, and meteorite. And as I've listed them here, they're kind of as they occur. So meteoroid is like the space rock. A meteor is that short-lived streak of light. And a meteorite is if something makes it through the Earth's atmosphere, then you pick it up on the Earth and it's a meteorite. Let's see, and then when we experience a meteor shower, now remember what a meteor is that streak of light that occurs as a meteoroid or some debris falls through the Earth's atmosphere and kind of burns up. So when we have you can on a dark night actually see one of those every 10 minutes. But when a meteor shower is where you see lots of meteors over the course of a given time period, maybe the course of a night or over several nights. But what's happening is that the Earth is passing through comet debris. So we kind of talked about that in class. So that comet debris is in the same place as the Earth orbits the Sun, so these meteor showers happen at the same time every year. Let's see, comets. So the anatomy of a comet. You need to know kind of coma. That's if we start with nucleus, that's kind of the rocky part of the comet. Then it kind of, to me, I think kind of fizzes this kind of spherical region called the coma. And then we actually have two tails, but as long as you generally know the tails, but there actually is a plasma tail and a dust tail. The next question is kind of related to tails, and tails will always be directed away from the sun, and we talked about this in class that the reason for that is because the sun's solar wind is pushing that tail away from the nucleus. So this is to say that even if it's always directed away from the sun regardless of the direction that the comet is going. Three types of asteroids, and they are by their location. So the belt asteroids are in the asteroid belt, of course, between Jupiter and Mars. Trojan asteroids, although there are more than just these Trojan asteroids, the most famous one, as I think of it, are associated with Jupiter. They're in Jupiter's orbit. They escort Jupiter around. And then we have these kind of miscellaneous Apollo asteroids that actually their paths take them across Earth's orbit. Then we go on to the next item is demotion of Pluto and the object Eris and dwarf planets. So this is kind of what I wrote in these three different colors. Basically, Eris was found in the Kuiper Belt, and it was either to classify Eris as the 10th planet or to demote Pluto and Eris down to a new category, a category of objects called a dwarf planet. And I personally am glad they took the latter approach. Kuiper Belt and Oort Cloud, they're both homes to comets, and the red arrow there is kind of pointing to that, actually the Kuiper Belt that actually lies in the plane that the ecliptic that the planets orbit the sun in, and then the Oort cloud is kind of, I've got it here in green. So Tunguska event, I double checked and I don't think I have this in my notes this semester, so it's going to be worth extra credit. Now the video we watched on comets and asteroids actually did talk about the Tunguska event back in 1908. It occurred in Siberia, and you can kind of see this picture up here with these downed trees. And it's thought that I've heard either a comet or an asteroid or a meteoroid actually blew up before it hit the ground. So, but it was a very explosive event back in 1908. Worth extra credit. Okay, so just a handful of questions about associated with Chapter 10. Chapter 10 was those extrasolar planets. So just in general, know that what an extrasolar planet is it's a planet that doesn't orbit the sun. So it's a planet orbiting other stars. And up here, I think I might have asked this on an earlier homework test, I'm not sure, but if somebody asks you, do most stars have planets in orbit about them, you say yes, yes ma'am, or yes sir. About 70% of stars actually have their own set of planets. And so how do we know, how can we see this? Well, we talked about actually most planets, I'll say all, but extrasolar planets are observed indirectly. And two indirect methods are either looking for the wobble. Actually, I've got here that our own sun actually kind of wobbles relative to the tug of Jupiter on it. So you can look for the wobble, and there's a couple of different ways to look for the wobble, but that should do it for you. And then the other way is if that planet goes in front of the star, you can actually see the star dim a little bit. So that's kind of an eclipsing phenomenon. I kind of put the word transit and eclipsing. So transit simply means for the planet to move in front of the star, and eclipse means, to, of course, for a little bit of the light to go away. And up here I've got in blue that the larger the planet, the more the eclipsing effect. I bet you buy that. And then there's a question on there about what properties can we gauge about these extrasolar planets. They are so far away, but you're like, really? You can do that? And honestly, we can determine the period. Remember, that's how long it takes for the planet to orbit the star. We can determine the distance between the planet and the extrasolar planet and the star. Eccentricity, kind of the shape of the planet's orbit. We can get to the planet's mass, its size, its density. In some cases, we can actually know the atmosphere around the planet. That's why some of the excitement has come up with some of these extrasolar planets recently. And we can know the temperature of the planet. So very exciting stuff. Chapter 11 was all about our star, the sun. And one of the things, there's a question on there about something called gravitational equilibrium. And I brought in this figure that actually you can kind of see the green arrows going in, that's gravity, and the red arrows going out, that's actually kind of that positive pressure associated with the energy that the sun is putting out in its core. So in the sun's core, well, it needs to be very hot and very dense, because only those with very high pressures, that's what I mean by dense, very high pressures and very hot, can we go ahead and have nuclear fusion occur. So that's very important. And actually those are the conditions in the cores of other stars as well. So how does our sun generate energy? And it's via nuclear fusion. Just in general, it's what we say converting hydrogen into helium. And the next thing there, actually related to that, is you need to know kind of the overall reaction of nuclear fusion in the sun's core. I had a slide that kind of said what you put in, which in chemistry we would call those reactants. You put in 4 protons. Oh, well, let me go ahead and add to this. When I say protons, those would be hydrogen. Or protons, I'll just put H. Think of those as hydrogens. And what you get out is 1 helium nucleus, 2 gamma rays. Let me go ahead and put energy there. That's your energy. All right. And you get these 4 cute little subatomic particles, 2 positrons and 2 neutrinos. And I don't have the statistic here, but our sun is doing a lot of that. It's definitely pumping out some energy. So then the layers of the sun's atmosphere and layers of the sun's interior. So you're going to want to kind of know those layers. And I brought in a figure from your textbook. How long does it take for... very good. How long does it take for the energy that's created in the sun's core to work its way out, especially in the radiative zone? Remember, that's that random walk. And I I was taking this from memory, so it might not be exactly right, but it's ballpark about 70,000 years to 120,000 years. That's a heck of a walk, you know, and that's for just that photon of energy to work its way from the core out to the edge of the radiative zone. It goes through the convective zone, quickly through the photosphere, and then it takes about 8 minutes to reach the Earth. I think that is so cool. Here in purple, I say, what are sunspots? Speaking of cool, sunspots are kind of dark regions on the sun. They are generally cooler regions. And sunspots, then, remember we saw in the video where basically you can kind of think of a magnetic field coming out of one sunspot into another sunspot. So you want to know, you need to know features of an active sun. Just be able to kind of list these out. So we have sunspots, solar flares, prominences, coronal holes, coronal mass ejections. That last one are the big ones, the CMEs, coronal mass ejections. So those are all associated with what we call an active sun. And then in general, the sun's activity varies. We call it the sunspot cycle, but it's just the solar activity cycle. And it varies with our 11-year cycle. And the reason we have the sun kind of winds itself up and then kind of unwinds itself has to do with this actually it's called differential rotation, but the winding up of the magnetic field lines. So you might want to know that for the test too. And then we finished up looking at just stars in general. We'll be definitely talking more about stars in Unit 4. But one of the big things that affects a star is its mass. And so actually, and it's a little bit counterintuitive, maybe, maybe not. Up there at the top, I put low mass stars and high mass stars. And in Unit 4, we'll kind of say, well, what mass kind of differentiates the two types of stars. But just for now, think of high mass stars as being hotter, being brighter. And this is a little counterintuitive, that high mass stars will live shorter lives, but it is very much true, and we kind of went over that a little bit in lecture. Okay, and more on that later. Luminosity was the output energy of a star, and it's measured actually in watts. Brightness, I missed an S there, but brightness is then actually how much energy reaches Earth. So brightness sometimes is called apparent brightness, sometimes it's called apparent magnitude, a lowercase m. And then actually remember, luminosity is what the sun or star is putting out. Brightness is as we see it, and kind of the link there is the distance. So as you know that the farther away an object is, then the brightness is going to go down, right? So actually it's got an inverse squared relationship. So here are three quantities that relate luminosity, brightness, and distance. So pick your favorite quantity, or put all three quantities on your note card if you want. But these are all talking about how these things vary. The next line there, actually I kind of said a couple of slides ago, apparent magnitude, lowercase m, is the same thing as brightness. And remember that it seems a little backwards, that actually, for example, if you had a magnitude of minus 1.0 is actually brighter than a magnitude of plus 1.0. So kind of keep that in mind. It's based upon, or well, it's kind of, the scale is kind of based upon this, that the dimmest that you can see with your unaided eye, without binoculars or anything, is a magnitude of plus 6.0. Let's see. Binary stars, and I don't have it on this slide, but if I were to ask you, are there many stars up there that actually have a companion that makes them a pair or a set of binary stars? And the answer is yes. We think maybe 2/3 of the stars up there actually have a companion star. So the types of binary stars are actually set up based upon how they are detected. So up here, kind of clear over at the right there, I've got the 3 ways of detecting a binary star. There are visual binary stars where you can actually see them separated and see their motion. but those are not as common as the other two types of stars. I think that would be right to say. Spectroscopic star actually takes into account the Doppler effect. The red shift is something is moving away from us, and the blue shift is something is moving towards us. So actually, you end up seeing kind of this shift in spectral lines as a star is moving towards you and away from you, towards you and away from you, even though it looks like it's in the same spot. You can tell it's moving towards you or away from you. So that's a spectroscopic binary. And then my favorite probably is underneath it, the eclipsing binary, where you have a pair of stars. You can't tell you have a pair of stars until actually one star, if you look close enough, is eclipsing the other star as it moves in front of it. I think that is so cool. Then there are 7 spectral types of stars, and I told you you can use the O, be a fine guy or girl, kiss me. And then just remember that then O is the hottest and M is the coolest. And we'll be talking more about these HR diagrams. I just kind of introduced them in this chapter talking about stars. HR diagrams are great. You'll need to know what's on the axes. So the y-axis is luminosity, and actually we're going to see that absolute magnitude and luminosity kind of go hand in hand, so we can put either one along the y-axis, how luminosity, how much energy is putting out, and along the x-axis we have temperature. So those two things, temperature and spectral type, actually go together. Let's see, those are on the axis. The main groups, and I went ahead and just drew an HR diagram here. I know it looks really busy, but you can kind of see the main groups. Those kind of circles are clusters of stars. So when Hertzsprung and Russell started kind of making this, what we call a scatter plot, they could see these kind of groupings of stars. I think the main sequence star, kind of on that black line, are one of the most important. Our sun is actually on the main sequence right now. And that actually group of stars is in its main sequence. It's in its main type of actually burning hydrogen to form helium, just like our sun is. Then we have the giants kind of up and to the right, and the white dwarfs kind of down and to the left. And so those are 4 types of groups on an HR diagram that you kind of want to know. We'll be talking about more about how those are linked later. Okay, one of the things that says how are stars on main sequence, okay, arranged with regard to mass and luminosity. So the main sequence, remember, is that black line, and you can kind of see I've got in the upper left, I've got high mass stars, and in the lower right, I've got low mass stars. So that's how they're arranged on the main sequence anyway. The next item up there, I need to explain a little bit. Well, we haven't talked about this in lecture yet as I'm recording this, so I will talk about this. But we can use an HR diagram and focus on the main sequence, and we can get an understanding for how old that set of stars is. Now, I told you that on the main sequence, the high mass stars are in the upper left-hand corner. And then also on the slide, I said that the high mass stars actually live their lives faster than the low mass stars. As the high mass stars live their lives, and quickly, if they run out of hydrogen, basically, they will, what we say, move off the main sequence and move into the giant area on the HR diagram. So, so this is to say you kind of get this peeling off effect. And so the more stars that have peeled off, then that means that that star cluster is older, basically. Okay, and the point at which they have peeled off the main sequence is called the turn-off point. So there you go. 2 types of star clusters. So if you're into observational astronomy, then you can. These are embedded in your brain. They're just beautiful. A star cluster is basically a group of stars that were most likely born all about the same time. There are open star clusters and globular star clusters. And up here in, kind of squeezed it in here, I have next to the open clusters in red, it says open clusters generally are younger stars, and they are in the galactic plane, is what I tried to write there. Globular clusters then are older stars, and they are not located in the plane. They are located outside the plane of the Milky Way in a region we call the halo region, which I think I mentioned clear back in Unit 1.